So good morning and welcome back. So today we are finally in the position to add some further structure to a manifold. And we'll do this first on a principal bundle, and later on we'll inherit the structure to associated bundles. And so this comes under the section 5.4, and the topic is connections. And more precisely, this is connections on a principal bundle. So on a principal bundle, we had this right action of some Lie group G, and furthermore, it's a bundle, and it's a principal bundle we're looking at. And so there's some warning that usually, or probably you already met the notion of a connection in, say, differential geometry in general relativity, and there very often connection, the term connection is used synonymously with covariant derivative and synonymously with parallel transport. Well, you need to forget about this. So really a connection is a structure on a principal bundle. And then once you have a connection on a principal bundle, we'll see that this implies a parallel transport also on the principal bundle, and this also implies a parallel transport on any associated fiber bundle. And then there is a very special case, and that is if the fiber bundle is actually a vector bundle, then it can be used to define a covariant derivative on a fiber bundle which is called a vector bundle. So that is where the fiber carries a vector space structure. So you see in decreasing order of generality we have connections, parallel transports, and finally, as a hyperspecial case, covariant derivatives on a vector bundle which still is defined in terms of a connection if this vector bundle is the associated bundle of some principal bundle. Okay? So this is important because it's often used synonymously, and it could lead to confusion if one doesn't clarify it's not synonymous at all. Now, if you don't know about covariant derivatives, forget what I'm going to say, but for those of you who do, it may be helpful. The covariant derivative on a vector bundle, if you write down in coordinates, it's given in terms of some gamma symbols. And you know that they do not transform as a tensor. They transform as connection, well, components, covariant derivative components. Now the point is, and the beauty is, that a connection on a principal bundle will turn out to be something very simple, namely a one form on the principal bundle. So it's nothing special, okay? The point is you cannot localize, you cannot give a coordinate dependent form, well, a local form, without choosing a section, and we know that on the principal bundle we can only choose a global section if the principal bundle is trivial and so on. And this kind of thing will finally lead to some funny transformation behavior, okay? But abstractly speaking, the connection is just a one form on the principal bundle. However, we're now going to start defining what a connection is, and we will not immediately define it in terms of one form. We'll define it differently and only see that this is equivalent to choosing a one form with particular properties. So, but first we look at the following. So, so this was just the introduction, and so now let's look at a particular principal bundle P. Let this be a principal G bundle. Then this right action we have here induces a vector field on this principal bundle. So then each A that we take from the Lie algebra of the group G induces a vector field which we may call XA. It's a vector field X, and a vector field on P, on the principal bundle. We know that a Lie algebra element induces a vector field on the group by the exponential map. But now we want to induce a vector field on P. This vector field on P is supposed to be called XA, and we define it by defining it at each point P. So for all P in P, it's defined as follows. Well, by its action on a function f on P, as follows. This is supposed to be f at the point P, but the point P acted upon from the right. We need a group element that acts from the right, but we just have a Lie algebra element. Well, of course, we get a group element by exponentiating the Lie algebra element, but we want to look at the entire one parameter family of subgroup here, and thus we get the function evaluated along a curve in P, because we start with the point P and this thing pushes us further along this curve. Then we take the derivative with respect to this parameter t here, okay, and we evaluate at t equals to 0, which means at the point P, and this defines this vector field. Okay, so right, and it's useful to introduce to define a map, let's call it I, which actually affects this, which takes an element in the Lie algebra, this A, and assigns to it the vector field I just defined on P. So it's a section of the tangent bundle of P, simply by assigning to A the entire vector field XA here defined on P. Okay, so we have this this map, and this map is which can be shown to be a Lie algebra homomorphism. Because clearly this is a Lie algebra, I can actually take two elements, A and B, in this Lie algebra, and this bracket is the bracket, the Lie bracket on TEG that we constructed. And I can take the result and map it by I, and I find that I could have mapped the individual Lie algebra elements by I, and then taken the differential geometric Lie bracket of the resulting vector fields. And this, of course, constitutes a Lie algebra homomorphism, and we're going to use this. Okay. Now, there's another definition. It's going to be essential. And that's the following. Let P be an element of the principal bundle. Then we define the so-called vertical subspace, which is a at a point P, which is really a vector subspace of the tangent space at P. So this is really supposed to be a vector subspace, not only a subset. It's a vector subspace. We define this to be the kernel of the push forward of the projection pi, which is the bundle projection. And you remember that the kernel is nothing but all the elements in the tangent space at P, such that the push forward, which is a linear map, takes this to 0. The kernel is all those elements that are taken to 0 by the linear map mentioned here. That's the kernel, and this VPP is called the vertical subspace. At this point P. Okay. Now let's try to get an idea of how that looks like. So pictorially, what is the principle? There's already the slow chalk. Okay. Okay. So if you draw a picture locally, so these pictures usually only work locally, there's a piece of the base manifold, and our principal bundle consists of attached fibers of the group at each point, right? So a principal bundle locally looks like this. And now let's think, what does the pi projection map do? It takes a point from here and projects it down to the base point, right? Okay. And now the question is, what is the vertical subspace at a point P here, for instance? Well, the answer is it's this entire fiber, of course, because you remember that the push forward, so this is pi, but the push forward of pi takes a vector that's attached here and pushes it down here, right? So the question is, what about, say, this vector here? What happens to it under the push forward of pi? Well, one way to think about it is to think about a curve to which this vector is tangent, then to project the curve, which is not done by the push forward but by the pi. You project this to a curve into the base manifold that would then look like this, say. So if the curve is run through like this, and we know that the push forward of a tangent vector is the tangent vector of the projected curve, of the mapped curve. You remember that? So here it would be mapped to, say, this guy. This here would be mapped to this guy, and obviously this is not 0. It's not a 0 vector. So this guy here does not lie in the kernel of the push forward of pi. But what does lie in the kernel is every vector that points like so, because this can be seen as, even if it's a tangent vector to a curve that looks like this, you push down the curve goes here and it goes back again, but then at this point here, the tangent vector to this curve is also 0, and so this guy lies in the vertical subspace. Okay, so and that is why it's called the vertical subspace. So once one realized this, one understood the push forward of pi, it's obvious it's the fiber. Okay, that's the vertical subspace. Okay, so we have a little lemma, and that says that what we constructed before here, this vector field XAPF, XA, so for every P in P, the XA P we just defined lies in the vertical subspace of P. Well, the proof is almost, well, it's absolutely immediate. We saw that XAP was that vector field that actually was generated by pushing forward this point P by this one parameter subgroup and evaluating here. And it's clear that this curve here, this is a curve gamma of T, right? This lies entirely within a fiber. Within the fiber pi inverse of pi of p, right? Because action on a certain point by the group only pushes the point in the fiber. We used this several times already in these lectures. So that lies entirely in there. That means if you look at this curve here, it lies entirely within the fiber, but hence it follows that the push forward of this vector xap under pi can only lead to the zero vector here in the tangent space to the base manifold, but that means that the xap is an element of the vertical subspace. Okay, that's it. So what have we seen so far? Well, we used nothing but the principal bundle structure, in particular the action of the Lie group here, and we were able to construct for each element in the Lie algebra a vector space or many vector spaces, not any A in the Lie algebra, which however all lie in the vertical fiber. These are vertical vector fields, and they are given by the very structure of the principal bundle. Okay, so far so good. Now, this is something we're going to use, but it's not what we actually need or what we want. What we want and the idea of a connection. Now, the idea of a connection is to make a choice. And you know that whenever you make a choice, you introduce structure, and this structure will be called a connection. The idea of a connection is to make a choice of how to, and that's where the name comes from, how to connect the individual points of neighboring, also in quotation marks, neighboring fibers in a principal bundle. So again, pictorially, what we want, and that is going to be extra structure, is the following. So we have again our local picture of the principal bundle, where at each point of the base manifold there is a fiber that's isomorphic to G attached. And now let me draw two nearby fibers, but of course you have to think of them as being very nearby, and that of course is supposed to, well, anyway, thought of in a topological way. Now, I would like to be able to say this point here is to be identified, well, or is to be, well, to be identified or to be associated with this point over here. So in walking from here to here, which point in this fiber do I call to be the same as this point here? It's a very, very normal notion. Well, not being in the fiber bundle, but if I'm here and I say, well, I have this direction, which is this tangent vector, and then I have this idea that if I walk over here, that this is still the same direction. But what does it mean? Because it's a tangent vector in a very different place. Okay, and similarly in a principal bundle, you would like to be able to talk about this point as to be identified with this point. Now, obviously, I could have chosen something different. I could have said, well, no, this point is to be identified with this point, not that one. Obviously, there is a choice. Now, what do we mean by nearby fibers? Well, we mean a linearization. That means if I'm at this point here, P, and I look at this subspace here, which is, of course, VPP, it's the vertical subspace at this point P, then I make a choice, and that is the choice I'm talking about. I make a choice of another subspace, and this is a 1 + 1 dimensional picture, but this is supposed to be another subspace such that the VPP and the direct sum of the HPP span the entire tangent space at this point. Okay, so I choose an entire, a complementary subspace here, HPP. And of course, I could have chosen a different one and a different one. The only one I cannot choose is the one that lies such that it intersects this VPP so that it's not a complementary subspace. Okay? And now you see, of course, this is a subspace of the tension space at this point, so it's an abuse to say that this arrow points to this point in the fiber, because it doesn't. As little as a tangent vector on the surface of a sphere points to another point on the sphere. It doesn't. It lies in the tangent space. However, it's the linearization of the idea. If you go very, very, very close, then the mistake you make by identifying this or by using the exponential map, right, you really hit a point very nearby. Okay, so that's the idea. So that's the picture you have in mind. But technically, we have here a vector subspace, and then of course, if we later on go to integrate and so on, then will be the idea of parallel transport. We can really say this point with exactly this point, because we integrate along a curve that is tangent to the such chosen subspace everywhere. Okay, that's going to be the idea. But here, the only thing you need to realize is that we want to make such an identification, and we need to make a choice to achieve that. Now, so that's the idea. But now we can, of course, or we have to write this down as a formal definition. So more precisely, or precisely at all, we have the definition. A connection on a principal fiber bundle, on a principal G bundle, sorry, P pi m, is, well, the technical term is a distribution, but that's not the distribution from functional analysis, the distribution from differential geometry, but I'll absorb this into the definition. Is an assignment where for every point of the principal bundle, where for every P in the principal bundle, a vector subspace HPP, that's just the name of the guy, a vector subspace HPP, of the tangent space TPP at this point is chosen such that, now there are two conditions, well, there are actually three, so let's go here. So the first thing is that you want that, as I said, that this HPP direct sum VPP, the vertical subspace, that they together constitute the entire tangent space at P. So it's the formalization of what I said before with this complementary thing. And then B, if you do that, well, let's go back to this picture here. You have to do this at every point. So you also have to do it at this point P down here. Well, let's call this the point Q. And you also make a choice. And say there the choice looks like this. Okay? And so you can imagine that you make a choice everywhere along this fiber, everywhere along here, and so on. And one thing we want to worry about is that this happens smoothly. So if you go up here, it doesn't jump, but it happens smoothly. And if you go from point to point, it also happens smoothly. This will be condition C. I'm not talking about this yet. But now let's stay within one fiber. I can reach this point Q down here. If I can reach this point Q by a right action of some group element from this point P. So let's say I have a point P. Now I have a group element by which I move to another point. Then I want this choice of this so-called horizontal, that's why the H is horizontal subspace, to be compatible with this right action of the group. And there the idea is that that if I act, so let's say I take any element of this horizontal subspace at this point P, how can I relate vectors that lie in here to vectors that lie in here? Well, I go from here to here by the right action of the group. But if I want to relate the vectors, I need to look at the push forward of the right action. Okay? So I take the right action of this group element G, and then I take the push forward of this, and the requirement is the push forward of any element in here, of the entire space here, should map to the entire space here. So the requirement is that this be the horizontal space at the point P acted upon from the right by G, P. That's the idea. So if I move the base point by group action, please map the entire horizontal space by push forward to the entire horizontal space. It's a very reasonable compatibility condition here, without which nothing would work. And then C takes care of what happens, well, within the fiber, but also if you go from here to here, this action should be smooth. Now, normally I would have said it's a smooth distribution. But so we said it's an assignment, and it's smooth in the sense that the unique decomposition which decomposes every vector that lies in the tangent bundle, in the tangent space at some point, decomposes this into a so-called horizontal part plus a vertical part. And it's clear that if you have a direct sum here, any vector in here has a unique decomposition into a part hor xp, which by definition, so how do we write this? Which by definition, which by definition lies in HPP, and a vertical part which by definition lies in VPP. So this unique decomposition leads for every smooth vector field on P to two smooth vector fields hor x and ver x. So it's these vector fields are defined pointwise by this unique decomposition, but if the vector field x was smooth, then individually the horizontal component of the vector field x at every point of the manifold and the vertical component, they are again both smooth vector fields. So smooth leads to smooth. That's the key point here, and that takes care of the idea that nothing, well, certainly continuous, but it's also smooth, this assignment. Okay. Yes?
What is VPV?
Sorry. P. It's the vertical subspace of the principal bundle at the point P. Okay? So this just formalizes the intuition we had here. Nothing more, nothing less. So there's an important caveat. So this decomposition in vertical and horizontal parts, both the vertical part of a vector at a point P and the horizontal part of a vector at a point P, they both depend on the choice of this horizontal subspace. So maybe by terminology one might be misled to think that maybe the vertical part is independent of this choice, but the horizontal part depends on it. Or maybe the other way around, maybe the horizontal part doesn't, but the vertical does. No, both this vertical and the horizontal part depend on this choice. Again, it's best shown in a picture. So say you have this subspace, which is the vertical one, which is defined canonically on a principal fiber bundle. But now, so there's the M down here. But now you're at the point P here, and let's say we look at this vector here. This vector. Now, say the choice of horizontal subspace, my choice of horizontal subspace is this one. No, could look like this. So this is the point P here, and this is HPP. And now it's clear that the decomposition here is into a vector here. So this be, if this is x, that's the vector, then this here is hor x, and this guy here, so this guy here is the vertical part of x at this point. And now take exactly the same vector, but I just copy the picture in order to not make this unreadable, but I now try to really take the same point P here and the same point and the same vector x. Well, it's the same, right? It's the same vector. But now instead of choosing the the horizontal subspace like this, I choose, as an extreme case, well, extreme case for this example, choose it like this. It's possible. And now you see that the vertical component of this x is 0. There is no vertical component. Okay, and the horizontal component also different from here, right? Because it's the entire vector, whatever that means. Okay, you got to compare, for instance, these two, this one versus this one. Okay, so in this decomposition, both the horizontal and the vertical part depend on the choice of HP. Aha. Now, the definition we gave of a connection as being a choice of a complementary subspace to the vertical space is geometrically very intuitive, very clear what we're doing. Technically, it seems a little bit tricky, because how on earth do I write down such an assignment? How do I provide it technically? Right? Well, we can talk about it. It's well defined, but it's difficult to write down technically. Now, that's the idea. Yeah?
On the left-hand side, you write the vertical of x on the VPP.
Yes.
But on the other side, it seems like it's a horizontal, or perpendicular to HPP. You know what I mean? So vertical.
No. So I wrote vertical here because, actually I should have written it here, right? But now, because this space is like this, the vertical component shrank down to 0. That's the idea. So think about this HP. In order to go from this picture to this picture, you might want to think about tilting this HPP until it's here. And while you tilt it, you see that if the vector is kept the same, that this projection to the vertical axis is a parallel projection, you see. So if you want to go here and you find the vertical part, you need to go parallel to this one to see what this component is, you see. And this shrinks to 0. This is what I mean here. And the horizontal part, well, that's this vector x. So in this case, hor x reproduces x. Right? And this is a different situation to here, where here the hor x doesn't reproduce the x and the ver x is non-zero. But everything's kept the same. It's the same fiber at the same point. So this is pi of p. This is pi of p on the base manifold. The same point, the same vector, but a different choice of horizontal space changes both ver of x and hor of x. That's the only point I wanted to make. And it's important to realize. Further questions to here? Or? Okay. So now again, assigning a horizontal subspace to each point is geometrically very intuitive. It's technically, it's a different matter. So technically, the choice of a horizontal subspace, I didn't introduce this terminology in writing, but I said it several times, of a horizontal subspace HPP at each point P in P in order to provide a connection is conveniently encoded in the thus induced Lie algebra valued one form. Lie algebra valued one form omega, and we define it at every point P of P, and there it takes you from the tangent space of P that makes it a one form in linear fashion, makes it a one form, to not the real numbers, but to, and that's the idea of the Lie algebra valued one form, to an element in the Lie algebra of the group. How? It does so by taking a tangent vector to the principal bundle, and it maps it to omega of x, okay, all right, so it's a vector at the point P, omega P at xp, and this is defined to be, well, we first look only at the vertical part of the specified vector, and so at this point we might think this has nothing to do with the choice of horizontal subspace, but of course it does. That's the contents of the caveat I gave, right? So in this vertical of x is already information about the horizontal subspace, but this guy here will then be an element of the vertical subspace, okay? Take an element of the tangent space, that vertical subspace, but I want a Lie algebra valued one form. Well, I take the inverse of the map I defined in the beginning. So if we recall what this map I was a map that took you from the Lie algebra into the tangent space TPP by virtue of assigning to A the vertical vector field generated this way. That's the I. Now we know that because this A is taken into XA, and this XA is always a vertical vector field, as we showed in the beginning, we know that actually the image of this map is only VPP. Right? It's only VPP. And indeed, this is invertible. Essentially why? Well, because our Lie algebra always maps diffeomorphically into a small region of any point of the Lie group, and the fiber, the vertical fiber, is the Lie group. So this is actually a vector space isomorphism, so you can go backwards, and that is what we're using here. And what you therefore get is in the end an element of TEG, which is precisely what we wanted. Okay, so this is an extremely important definition. This takes the choice of horizontal subspace hidden in this ver, in this projection of the vertical part, and by this canonical I map, or its inverse, maps it to the Lie algebra. So it takes this choice and makes it into a one form. Yeah?
Yeah, I think I pointed to gamma TP and not to VPP, so don't we need an index P for the I or something like that? Or, yeah.
That's a very good observation, and because I went to every individual point, that's true. Yep, thank you. It took an entire, mapped this to an entire vector field, but then in particular, I can look at it at the point P. That's right, that's right. Okay, so we can have take this thing, and this is then called, and note, it's a one form on P. One form on P. It's not a one form on the base manifold. No, no, no. It's a one form on the entire principal bundle, and this is called the connection one form. Connection one form with respect to the connection. Okay, so the connection is a choice of horizontal subspaces, and once I have such a choice, I can define this form. So it's the connection one form with respect to a given connection. The connection being hidden in this ver. Okay. So how do I, so that means given the horizontal subspaces, I can construct this form. How do I get back the horizontal subspaces? Observation. The horizontal subspace at a point P is then recovered from the omega as the kernel of omega at this point. So whatever, so I again define the kernel, you know what the kernel is, maybe it's nevertheless useful to write this down here, is all those x in the domain in TPP for which the omega, which are sent by the omega to 0. So from a choice of subspace, I define a form, but once I defined the form from such choice of subspaces, I can recover the subspace as the kernel of this Lie algebra valued form. So far, so good. Now it's clear that only because the form is precisely defined like this do I get this. Not every one form on P can be given and then I take the kernel and I get an HPP. Of course not. Only this very specially defined form like this. What we're now going to do, we want a complete replacement. For this HPP we had 3 conditions, right? How it was to be chosen. We now want to find out what are the properties of this one form if it's defined like this. And then we'll see that we can elevate these properties to a definition of a connection one form without giving a connection first, but a one form with certain properties. And then from it we can recover HPP in this fashion, which then automatically has the required properties. So that we can think at the end alternatively of HP choice with certain properties, or of a choice of one form on the principal bundle with certain properties. Okay. A connection one form omega with respect to a given connection has the properties A. If I take the connection one form and at a point P and I apply it to this vector field XA, or the thus induced vector at the point P, which we got from acting, well, we had this definition from of this vector field on P that's generated by an element of the Lie algebra, then the connection one form yields the Lie algebra element A. That's just it. So in a sense, before we had this map I, so let's again remember, we had this map I which took a Lie algebra element and sent it to the vertical subspace as we just saw. And now we see that if we apply our omega to this vertical subspace, we know it's Lie algebra valued. Well, actually, omega acts on the entire tangent space, but in particular, it acts on this vertical subspace. So you can say that's the restriction of the omega to the vertical subspace anyway. Then we get back the element A from the tangent space that we put in. So that is omega after I. And this says nothing but omega after I restricted here is the identity on the Lie algebra. So in a sense, applied to this vertical subspace, the omega is the inverse of this I. And of course it is, because we defined omega to be the inverse of the vertical part. Right? And that makes this restriction. So, yeah. Right. Okay. It's just to think about this. It's a comment. Aha. So that's the first property. And the second property, we had this idea that if we push along the fiber with a group by a right action of a group element, then the push forward of the horizontal space is the horizontal space at the other point. This must be reflected on the one form, so we certainly have to think about the right group action, but now how it acts on the one form, but now you know that can only be by pull back, not by push forward, but by pull back, because this acts on P, so this acts on the cotangent space of P, so it can act on this omega. And so if you take the pull back of the one form and look at it at the point P, and then you can plug in a vector xp, then the property is, at first sight it looks a little funny, well, funny, complicated. It's the push forward of the adjoint of the inverse G. Now it's the push forward because it acts on the omega P of xp, which is a Lie group element, a Lie algebra element, so this lies in TEG. Aha, but the add G, we recall, what was the add G? The add of some G, not G inverse, adds of some G, took you from the group to the group by taking an element H and sending it to G, H, G inverse. But that meant that the add G push forward took you from TEG to TG on EG, no, to TG identity G inverse, but that's again TEG. Ah, that meant the push forward of the adjoint really takes you from here to here. And indeed, this is an element in here, and the adjoint of G, well, in this case G inverse, takes you back to a Lie group element, which is exactly what this guy is supposed to do, because you pull back the form, then you again have a one form, you act on a vector that must again lie in the Lie algebra. So, okay, this makes sense that it looks like this. Why exactly it looks like this, we'll see in a second. Okay, so this is this, and connection one form, and the one form is smooth. Well, so that's the C property, is that omega is a smooth one form. Now, more or less, this ABC corresponds to the ABC of the definition of the choice of horizontal subspaces. Well, almost. At some point, we're now going to do the proof. In order to prove that this is true, we need to first prove this is true, and then we use this here and so on. But roughly speaking, this is the analog, and I think one can see it from what's written there. Okay. Good. Okay, so proof. Well, maybe we formulate this Yeah, okay, let's do it this way. So proof. So A, this is simply true by the definition of omega, full stop, because this is a vertical vector that we established, and we know that if we plug this in here, we just reproduce the well. So omega of xa, well, all at p, we know this is in the vertical space, and we know the omega, that's the definition of omega, is I inverse of the vertical part of whatever has been provided. Okay, but this already is a vertical vector, so it's I inverse p of xa p, but the I took the a to the xa, so the I inverse takes this back to the a. Okay, so this is immediate from the definition of omega. That's a. So of course here we're now assuming that the HP choice and so on has the properties of a connection. Now let's look at this beast, and we first observe that the left-hand side is linear. That the left-hand side is linear in X. So in this slot here, why is that? Well, this is a one form. This is the pullback of a one form. You get a one form. A one form is a linear map. Okay. So that means we can prove this by decomposing this xp into a vertical part and a horizontal part, and we prove it for horizontal x and vertical x separately. Okay. So let's do B1. Let's say xp is in the vertical part, and obviously B2 will be xp is in the horizontal part. Okay, so how do we do this? Well, so we start on the left. We take the pullback of the one form omega, and that's supposed then to be a one form at p, and we act on it on a vertical one, but then we can always generate this vertical one from a Lie algebra element A. So if this is in here, then there exists an A in TEG such that X is XAP. Okay? So if it's vertical, we represent it like this. And now what we do is we use the definition of the pullback. What was the definition of the pullback? Well, it is this form that's being pulled back, but if I pull it back along here, this must be the form at P on which the G already acted, and that is applied to the push forward of this vector with respect to this guy. So this is G down push forward of this vector xa at the point P. Of course, the push forward will take us to a point P acted upon from the right by G, which is exactly on which this guy here can act. Now, there is a step that is a little technical, but not uninteresting, and I will move it to the problem sheet. And this step talks about what's in the bracket here. So it's again omega p acted upon from by the right. And it turns out that what is in the bracket here, if you push forward the thus generated vector field, you get a vector field, no surprise, and you can actually calculate from what other Lie algebra element this pushed forward vector field is generated. In fact, it's generated by add G inverse hang on, how did this work? It's generated by add G inverse acting on, we need a Lie group element on A. Push forward, push forward on A. Yes, I think that's right. So that's on the problem sheet. Okay, so the, okay, this is imaginable that it looks like this, and in fact it is like this. And if you then look at this, then you see, aha, this is again, and this will of course be then at P acted upon from the right by G. But now we know from step A, so this is now from step A of the same theorem, which we already proved, that the omega at a point just extracts the Lie algebra element that generates the vector field on which it acts. So this is actually add G inverse push forward acting on A. Now we can massage this a little, and we can write this add G inverse push forward of omega of XA. Well, we just rewrite the A as the omega of XA, which of course we can, because that's just the same thing backwards. Aha, but if we now compare what we did, we plugged in here an arbitrary vertical vector field, and it now appears here again. Well, that's at the point P here. Okay. Then we showed exactly what we wanted to show for the special case of the x being vertical. Okay? So that's this. So then B2 would be the choice xp is in the horizontal subspace. Well, that's the only other possibility. And by linearity, as I argued in the beginning, by linearity it suffices to show this separately. And now we look at the same thing again. We study the push forward, no, the pullback of omega at the point P, but now we apply it to this guy, so I call this x hor to emphasize it's horizontal. It's just emphasis, x hor at point P. Now again, we use the definition of the pullback. So this is omega P acted upon from the right by a G of the push forward, G push forward acting on x hor P. Right? Aha! But now this x hor P is of course an element by assumption of the horizontal subspace. But what do we know about the push forward of this right action of G of any element in the horizontal subspace at P? Well, we know by property B of the connection that this is an element of the horizontal subspace at P acted upon from the right G. Why was this? Well, why? Well, since the push forward of the entire horizontal subspace at P is the horizontal subspace at the point P acted upon from the right on G. That was one of the properties of our choice of HP. Aha, but now we have omega P acted upon from the right by G, and then now an element of HPG, but we know that this is 0, because every element in the horizontal subspace at a point is eliminated by the one form, connection one form at the point. Right? This follows also directly from the definition of the omega in terms of the HP. Aha, okay, but this 0 here can of course be written, albeit somewhat pompously, as the push forward of at G inverse of omega at the point P of x hor at the point P. Why? Well, because this omega P x hor P, for the very same reason, yields 0, and then the add G inverse push forward being a linear map acting on 0 yields 0. But then we again see that for every x Hor we put in there, we get we get this guy XOR P in there, which is again for the horizontal vectors is exactly this statement here. Okay. Well, and now that omega is smooth, let's squeeze this here. Omega is smooth because omega is I inverse after ver, right? That's how we defined it. Now, it was the requirement that ver yields a smooth vector field if it's applied to some smooth vector field. And the I inverse well, that is smooth because the exponential map is smooth. And so you have smooth after smooth is smooth. That's it. Okay, so these are the properties, these two properties of omega shown from the properties of the connection, which consisted in a choice of horizontal subspaces at each point. Okay. Now, well, this may scare one at first sight, but of course we had this before. And of course, it's much more convenient to say, well, you hand me a principal bundle, and now you hand me a one form with these properties. It would be nice if we could show the converse of this theorem, namely that any one form with these properties actually induces an HP P that satisfies the condition of a connection. But that is the case. Okay? The proof is very similar to this, and hence it will go to the next problem sheet without much help. Okay? It's really very simple. Just not writing it down. Okay, let me see. Yes. Okay. So we need to stop here today because I travel. Again, the philosophy is this. I hand you a principal bundle, and now after this is proven, after you will show the converse of this theorem on the problem sheet, namely that every one form on the principal bundle with these two properties defines a unique connection, right? It's much more convenient to give such a one form. And it's nothing else. A connection then can be defined to be a one form with these properties. And then next time we will see how this actually gives rise to parallel transport on the principal bundle, but then also to parallel transport on any associated fiber bundle. And once you understand parallel transport and you go to a vector bundle, then in the fiber you have additionally linear structure. You can actually transport a point and then take the difference to another point, and then you can write down a differential quotient. But in order to have a differential quotient, you need a minus. Well, that's the inverse, the additive inverse of a plus. So the fiber needs to be a vector bundle. So the fiber needs to be a vector space, so the associated bundle needs to be in particular a vector bundle. But on non-vector bundles, which are associated bundles to some principal bundle, you can still have parallel transport. So it is absolutely not true that you need a covariant derivative in order to define parallel transport, let alone a connection. And again, of course, for applications to physics where, or say in differential geometry, where you look at the frame bundle as the principal bundle, you will establish a connection on the principal bundle, and that will inherit parallel transports to all associated fiber bundles, in particular to the vector bundle, to the tensor bundles, to the spinor bundles, and so on. You can always get them from the connection on the principal bundle. And the same is true for, say, non-abelian gauge theory.